Let me show you another utility. Now think about this. What are the derivatives that we have had to memorize so far? All right, so let's see, derivatives, and I remember we should know, right? Okay, we know. What do we know? Oh, sorry guys, looks like I crossed it out. Well, we know the derivative of x to the n, right? That's nx to the n minus 1. Remember, we want to memorize ones like the derivative of 1 over x and the derivative of the square root of x in particular. We want to have those on the hard drive because we see them all over the place, right? We want to know the derivatives of, let's see, e to the x. We know that's e to the x. The derivatives of a to the x. We know that's a to the x ln a, right? And then the derivatives of all the trigs. So I'm not going to write them all out because that's a pain in the butt. So we want to be able to take the derivative of trigs. What are we missing? We're starting to miss some derivatives here. Let's see, if I'm going to take derivative of trigs, then by God, I better know the derivatives of the inverse trigs. So let's see if I can put this new tool to work in an interesting way. Let's say that I want to know the derivative of equals, what am I doing? I want to know the derivative of, say, arc sine. Let's keep it simple. All right, the inverse sine of x. So I'm going to do a little something crazy here. I'm going to let y equal the inverse sine of x. Now, I want to find its derivative. So I on the prize, when everything's said and done, I want to know what dy over dx is. All right? Well, not a whole lot I can do here, right? I'm kind of trapped. There's not a lot of algebra that I can do. And I don't know about you guys, but I'm not really interested in the limit definition with this guy, especially if I might be able to employ a new trick. Well, isn't this true, if and only if, because they're inverses, the sine of y equals x? True? No, wait, I know what the derivative of sine of x is. It's cosine of x. However, if I employ my new little tool here, the derivative of sine of y, now I'm going to take the derivative of the sine of y as though the y is an actual x. So I know that I'm going to get a cosine of y, right? And then I just cheat. I leave my little footnote, my calling card that says, took a derivative, had to cheat a little bit, sorry. And I get 1, right? Because the derivative of x is 1. So dy over dx is equal to 1 over cos y. Well, crap. Well, that doesn't do me any good, really, per se. Now, wait a sec. What I need to be able to do, remember, we started with a function of x. Its derivative needs to be a function of x. Wait, I'll bet. If I employ a little tool over here called the trigonometric identity, because sine squared plus cos squared equals 1, so I know sine squared theta plus cos squared theta equals 1. In a puff of algebra, can't I write cosine of theta as the square root of 1 minus sine squared theta, right? So I'm going to use that tool right here. I know that, whoa, I'm going to do this little crazy tree thing because I need some space. I know that dy over dx is going to equal 1 over the square root of, excuse me, 1 over the square root of 1 minus sine squared y. Now you may say, Ripley, why was that helpful? We're still in this is supposed to be a function of x because I started with a function of x and this is a function of y. Yeah, but I'm not afraid. Look at what I got sitting right here. Oh, sine of y is x. So I just stick sine of y equals x back into this equation and I end up with 1 over the square root of 1 minus x squared. Isn't that cool? That's kind of fun. Now, students will often say, well, Ripley, don't we have to acknowledge that this is plus or minus? Well, we do, except think about that. What do I know that arc sine of x looks like? Well, it looks like that. Remember this, guys? It goes from -1, comma, this is -1, comma, negative pi halves, up to 1, comma, pi halves. That's the sum total of the whole equation, and it's always increasing. There you go. Now, how about if I employ exactly the same thing, if y equals the inverse cos of x? I'm going to do exactly the same trick. I'm going to blow through this one a little bit more quickly, though. I'm going to differentiate, right? I'm taking the derivative of that thing, so I'm saying negative sine y equals, whoops, dy over dx, got to leave my calling card, equals 1. So dy over dx equals -1 over sine y. Now I'm going to use the exact same trick. Okay, look at the same trick. I know that this is equal to -1 over the square root of 1 minus cos squared y, right? I know cos squared or cos y equals x, so this just ends up being -1 over the square root of 1 minus x squared. That's a great tool, isn't it? Now again, Rivoli, is it plus or minus? Well, look at your function, remember? Inverse cos. Wow, that's a badly drawn function. Looks like that. Remember this guy? All right, so this thing's always decreasing, so that's got to be my derivative right here. Now let's knock this whole thing out. How about the derivative of the inverse tan? Inverse tan is actually more fun of x. All right, why is that -1 there of all places? Let's make up my own notation. Ding dong. Okay, so same trick. Here we go. I'm going to do y equals inverse tan of x. Very helpful. I know that tan y equals x. Differentiating with respect to x. However, I'm not afraid. I know that the derivative of tan y is going to be secant squared y because I've memorized it. dy over dx, that's my calling card, equals 1. Doesn't that imply that dy over dx equals 1 over secant squared y? Now, hopefully you remember back in pre-calculus when I was waving my hands in front of the class and acting like a fool and saying, memorize your Pythagorean identities, memorize your Pythagorean identities. Well, here's why. 1 over secant squared, if you recall that secant squared equals tan squared plus 1. So this is just 1 plus, I don't know what that is, tan squared y. But I got to turn it back into a function of x. It started with a function of x. Its derivative should be a function of x, but tan y is x. So this guy is simply 1 over 1 plus x squared. Isn't that cool? We got to take our new tool, the implicit differentiation tool that we just learned, out for a test drive, and not only was it helpful for us to be able to figure out slopes of lines tangent to not function, but now look at this. In my armory, I've got 3 new derivatives. I know what the derivative of arc sine is. I know what the derivative of arc cos is. What the derivative of arc tan is. That's awful nice. I could do, I don't want to bore you with this, but if somebody put a gun to my head, I could actually take the derivative of the arc secant, the arc cosecant, and the arc cotan. And I wouldn't be afraid because I got this new awesome tool. All right, that's it, you guys, for section 3.6. We're going to do a bunch of these, so don't panic, as always. And we're going to talk in class a little bit about something called orthogonality, which I'm going to lecture to you for a few minutes on that. But other than that, thanks for your time and attention, and have a really good day.